Well, hello, good morning. I'm Terry Mahoney. Just to be different, I'm not a PhD student of John Beckman, and I'm still doing my thesis. I'm here to talk about something completely different, and continuing the Monty Python theme, I'm going to talk about Tycho Brahe and his collaboration with Johann Kepler. And for me, that's a bit like the Monty Python sketch, Summarize Proust. You just can't do it. So I'll have to stick to some very broad highlights, but I do want to make very clear indeed what it is exactly that Tycho Brahe did that enabled Kepler to find his first two laws. Well, now how do we... Okay, so I think, can you hear me?
Yeah.
Yeah. Okay, so I think Kepler summed up what it was that Tycho Brahe did much better than I've seen anybody else do it. Tycho Brahe conquered all feelings of fatigue and tirelessly pursued objectives generally regarded as unattainable. This is shown by his highly precise methods of observations in which he fought against the very nature of vision and emerged victorious. This is from Kepler's famous science fiction novel, Somnium, which was published 4 years after his death. And to English people, they will recognize two names in that arch. There's Guildenstern at the bottom, and at the bottom of the arch is Rosencrantz. And we're going to see this theme that is very evocative of the play Hamlet, Shakespeare's Hamlet. Well, let's talk about cosmology as it was understood in the 17th century. Now, Tycho was a Paracelsian. He had worked with one of his uncles in the Hereward, what was it? It was a Cistercian monastery originally, but it was now converted into a humanist center of learning. And the idea behind it wasn't just Paracelsus, it was a general idea at the time. The universe was one. Man stood in the middle as the microcosm of the greater macrocosm. At that time, we have to understand that according to the beliefs at the time, God permeated everything. This wasn't just the church imposing its will. This was a generally accepted intellectual idea. God permeated the universe, and the universe was directly connected to man through the astrological, not astronomical, the astrological aspects. Therefore, astrology was a fundamental subject that had to be learned by doctors. I mean doctors of medicine, because they had to apply astrology to the condition of their patient. So it wasn't just a question of what are the stars telling me today. It was of fundamental importance. The stars influence directly the human body. I don't want to spend too much time in this, but you can see here, you have a man looking down, and have a look at what he's sitting at what's underneath him. This is this here. This is a laboratory, an alchemical laboratory. If you like, it's a precursor to today's CERN. The idea that Tycho had was that one must study the components of the Earth, and by studying those, it gives you an idea of what's in the heavens. And if you study the heavens, they're similarly related to what we have beneath our feet. Everything was one. Okay, I don't want to spend more time on that because otherwise we're not going to get on to what's important. So in May of 1576, Tycho was granted the fief of the island of Hven by Frederick II, King of Denmark. And on this island, almost in the center, you can see the little quadrangle of what was to be Uraniborg Observatory. And here's the observatory, a wonderful building, and you can see straight away, without looking in detail, that the towers were necessary in order to house all the various instruments. Tycho had a huge number of instruments, and he was constantly developing these instruments. This was actually the first modern observatory in the sense that we understand an observatory today, where not only observations are made, but there's an active program of instrument development and instrument improvement. And this is a key thing with Tycho Brahe. There was such an overflow of instruments that eventually, several years after, in 1584, he needed to build yet another observatory to house all the extra instruments. I haven't got time really to talk about the instruments, but we can't avoid talking about the mural quadrant, because this is the quadrant that everybody knows about. I've chosen this illustration from Tycho's own History of the Heavens, a book which was edited after his death, because it avoids all the clutter that you normally see when you see copies of this instrument. It was, there you can see where the arrow points to the west wall of the ground floor of the southwestern ground floor room. And the blank space is a wall. There were 3 observers. There was someone keeping time, someone actually observing, and someone writing down the observations. But that was transit work. But there also, he had quadrants which could revolve. He had a wooden one and a great steel one, which could be used for azimuthal observations. The beauty of these was that you would always be able to calculate what the atmospheric refraction was. There was a great equatorial armillary, so that was actually aligned with the poles. So there you have one of the very first equatorial mounts. There were other instruments, such as sextants, which could be used vertically so that you would know what the atmospheric refraction was. But normally, a sextant and also many of the quadrants would only be used to measure the distances between stars, and you would not know what the refraction was because you had no way of measuring the altitude. So, refinements. Let's again listen to what Tycho himself says. Only this I wish to state here with regard to both this instrument and to the others, namely, that all of it has to be as nearly perfect as is possible in every aspect, and that therefore one should employ skillful craftsmen who know how to carry out the sort of work artfully, or else can learn how to do it. And if they do not hit the nail on the head first time, as they say, the constructor must not let himself be discouraged, but must have the work repeated and improve the defects in every way until none is left. He wasn't slapdash. Everything had to be as perfect as it could possibly be. And here is one of his breakthroughs. Normally, in astronomy, before the telescope, you would use a sight which had holes at one end, at both ends, and you would look through the holes and you would view the star through the hole. Obviously, if the hole is too small, you're going to get diffraction problems, but if it's large, you're going to get parallax problems. So he got around this by a peg and slit arrangement. If you look at the figure on the right, you can see you've got letters AD, there's a slit there. You would look through that slit and along EH in the distant one. And then you would go to the other slit on the right-hand side, and if you could see the star in both slits, then you had it centered. There was no parallax. There was no parallactic error. And if you were viewing the sun, you would let it shine through the hole, and there would be an inscribed circle on the inside plate of the bottom plate there. And it took considerable skill for the observer to get the sun centered on that circle. It was through this particular instrument, for this sighting, that Kepler was able to achieve the accuracies that he did. Well, it was one of his techniques. The other technique was the use of transversals. He picked this up, I believe, from a previous place that he had visited. And the idea was, there you can see you've got a 2-degree arc split into 30-minute intervals, 10-minute intervals, and if you want a 1-minute interval, you have to look for the space between the dots. And Tycho claimed that he could get down to 5 seconds of arc. There's no reason to disbelieve him, I don't think, because the arcs tended to be very, very large indeed. Now, if we look at his instrument development, if we take a look at how he used his instrument to observe the sun, you can see that with the exception of the year 1590, there was a gradual improvement in the precision of the observations. These are averaged observations. Unfortunately, Wesley only averaged the observations. He didn't take their standard deviation. I've highlighted in red in the 1595 measurements, because you can see that something very serious happened, especially with the equatorial arminery. I think Tycho was having very serious problems, political problems with court at the time, and things were all shortly about to fall apart. So how accurate were his observations? Well, we have voluminous observing logs, and what we have to bear in mind is that Tycho uses a very crude model for atmospheric refraction, and above altitudes of 20 degrees, he regarded there not being any refraction. So what the modern historian has to do in order to recreate the observations, to find, he has to take the average atmospheric conditions at Wien for a particular time of year and apply those to the time of observation at the time the time of year that Tycho made the observations. So here we have some results. I haven't got time to go into it, but they're quite fascinating. You've got Ptolemy's catalogue. This is 1,024 stars. And you can see that I've written down there as the standard deviation is around 10 minutes of arc for Ptolemy. If you're wondering what the sinusoidal arc is, there's no time to discuss it, but there's actually a scandal attached to this. Someone called Newton, not Isaac, has tried to besmirch the character of Ptolemy by saying that he stole the ecliptic, the obliquity of the ecliptic from Hipparchus and passed it off as his own. Now, that's a different story that I can't go into. But if you go to the right-hand side, you can see that now we're talking about a standard deviation of around 1 minute of arc. That's an order of magnitude improvement over Ptolemy and all Tycho's contemporaries. Very few people were making accurate observations. And if we talk about that, those were for latitude. For longitude, again, there's a complication. The thin line, which shows a sort of quasi word escapes me. Well, the distribution it's a narrower distribution, and you can see the sigma there is 1.5 minutes. And that's for Tycho's well-measured stars. There are just over 700 stars that he measured very accurately. But given that he had to vacate the observatory because of political problems, he decided that he wanted to make up the number to the standard 1,024, and he put in a lot of fainter stars, which were less well observed. They needed more repeated observations, which he didn't have time to do. So basically, he spoiled his own results by adding substandard data. But if you stick to just the good stars, that's the narrower distribution, you can see that the sigma is 1.5 minutes of arc, and that, if you include the more poorly observed stars, it goes to 7.5 minutes. And this is astonishing. I found it extremely hard to believe, but I have respect for the person that produced this graph. All this is taken from Michael Rosa's article that he produced for a conference proceedings held in Prague. There you've got Polaris, which was measured endlessly by Tycho. He had over 1,700 measurements. And you can see that the positional error, if you compare it to FK5, is of the order of a second of arc. Now, you might think that's totally unbelievable. I think what Michael Rosa, if I can ever find the man, he's disappeared. If I ever see him, I shall ask him to expand upon how he arrived at this. So you can see that the straight line shows how that's the FK5 line. The circle, or the circles, are all 1 minute of arc, and Tycho's observations are the dots clustered around the line. as for the planets are harder to observe because Mars isn't always available, but when it is, Tycho took as many meridian observations as possible. The U-shaped curve is the path of the planet during a night's observations. And at the bottom, you can see the observations clustered at the bottom of the U-shape. That's where Mars reached meridian. And several observations were taken with several instruments. The line at the bottom is the refraction-free line. And there turns out to be a roughly 8 minute of arc difference because of refraction. But basically, his planetary observations were between 1 and 2 seconds of arc. This is the state of astronomy before Tycho Brahe. So you had the Prutenic tables. If you use the Prutenic tables, which are based on Copernicus, the straight line is where Mars should be. And what you see is that Mars is hardly ever there. And if at one particular point, sometime in 1594, Mars was almost 5 degrees away from its position, where it should have been. So Copernicanism, in terms of the planets, really wasn't much better than Ptolemaism when it came to predicting the positions of the planets. It had no predictive power whatsoever. Then Kepler comes in. Kepler's work on Mars was all done in a book called Astronomy Nova, published in 1609. And as far as I'm concerned, the heliocentric debate ended with the publication of this book. And I shall explain why. Now, the title has given rise to a great deal of controversy, and I'll explain later that if you want further information on this, you need to refer to chapter 5 of a book that's shortly to come out. How am I doing for time, Johan?
1 or 2 more minutes.
2 more minutes, oh, yeah, right. So what did Kepler do? Well, he chose Mars because basically it's easily measurable. The eccentricity is easily measurable. It's a very eccentric orbit. The period is short enough for multiple apparitions of the planet during opposition, so you can get accurate observations. So compared with Mars's observations, with the calculations based on circle-based systems, Ptolemaic, Copernican, and Tychonic, the longitudes and latitudes, as we've seen, are hopelessly wrong. They're useless. Kepler, so he tries circles, doesn't work. He tries ovoids and finds an 8 minute of arc discrepancy. But 8 minutes of arc, as far as Kepler is concerned, was outrageous. That meant that ovoids could not be the solution because the error that they give was far too large for any error that Tycho could possibly have committed. So eventually, he fits his famous ellipse, and once he's done that, the longitude and that error now drops to less than 1 minute of arc, and the latitude problem is completely solved. So from Copernicanism, we arrive at true heliocentrism, because the Copernican system isn't actually heliocentric, it's quasi-heliocentric. The actual center of the Earth's orbit is the center of the Earth's orbit, not the sun. And heliocentrism, with Kepler's laws, is finally given what you could call predictive power, which it didn't have before. So there were 2 laws. The first law was that the orbits are elliptical. That was the first law discovered. And the second the equal areas law was the first law discovered, and then that the orbit was elliptical was discovered later. And you can say that the sun occupying one of the foci of the ellipse was actually a different orbit. Now, there's a lot of biographical detail which I would love to talk about, but I think Johan is going to lose his temper, so we won't do that. I just want to mention and if you want to go and see Uraniborg, there's a nice big hole in the ground, and that was thanks to King Christian IV and his councillors. So they did a wonderful job. This is a book that I've co-edited with two quite important, very important Kepler studies. It'll be coming out soon, so anyone interested, can talk to me if you break about that.
Thank you.